Yeah, I mean, maybe I'm coming from Münster, as you might know, yeah, but I'm also noticed a little bit later, yeah, I'm also related to Münster in a different way, actually, because what you not might know is that my PhD advisor was Joost Eschenburg, yeah, giving the first lecture this week, yeah, and so I was, well, he was not only my PhD advisor, but when I was a master student and attending courses in differential geometry, yeah, I was there, and then of course well, now I can see that was a part of your influence. So yours, of course, kind of, yeah, influenced myself, yeah. So, and I'm very happy about that. It's a different connection with that, it's kind of, which I only realized later when I was a student. I did not. Okay, so let me come to the talk. So in this talk, which joint work with Ramiro La Fuente, so Mn Gt, 0 capital T, will be a maximal homogeneous Ricci flow. Yeah, meaning that, of course, this one parameter family of matrices satisfies the Ricci flow equation for some initial metric G0, and the initial metric naught will be homogeneous, meaning that the isometry group of the initial metric G0 acts transitively on the manifold Mn. Yeah? Then, of course, it's very easy to see. Manifold is complete, and of course has bounded curvature. Yeah? Each point looks alike. Yeah? Therefore, in the set of many metrics of bounded curvature, there's a unique maximal solution to the Ricci flow, which either exists for all times, yeah? Capital T is infinite, that's called immortal, or capital T is finite, we say finite distinction type, and well, it's known that at the finite distinction time, the curvature of the matrix GT blow up at one point, well, because of homogeneity, it's going to blow up at any point, so therefore we cannot extend the flow past time capital T, so it just stops there. Now, in this situation, you have uniqueness, and for that reason, you can easily see that the Ricci flow does not lose any isometries, yeah? So it does not get worse, yeah? Meaning that the isometry group does not change over time. Well, there's a nice result by Stefan Gottschalk in general, yeah? First, you show, well, you don't lose any isometries, but you don't gain new isometries, yeah? So it's constant over time. So that's a maximal homogeneous Ricci. So my startup theorem is, which I'm not going to really go into, but just to give you a feeling what the curvature does, yeah? So this is joint work with Mice Simon and Miro. Yeah, so pick any time in 0 and t, and then we have curvature estimates. Yeah, I mean, all geometric quantities I'm talking about are, of course, all norms are constant functions on the manifold. Yeah? With respect to the metric GB, can be bounded. The maximum 1 over b and scalar curvature of E minus scalar curvature of 0. Yeah. It's not so important, yeah. I'm gonna draw the corollaries from that, yeah. Important somehow at this point is only, let me mention this, that the constant Cn, yeah, is of course positive, and it's not going to depend on the manifold, the homogeneous space, nor on the algebraic structure. Yeah. So in, say, dimension 7, there are infinitely many homotopy types of simply connected homogeneous 7 manifolds. There are many, and even dimension 3, there are uncountably many homogeneous structures, yeah, different homogeneous structures. Same manifold, but some homogeneous spaces. Does not depend on that thing. In particular, it does not depend on the initial dimension. Yeah. So it's kind of uniform only on dimension. Yeah. Okay, so yeah, not so important. What is important is, of course, we learned this from Valentino's talk. There are two cases which are very different: finite extinction time and enormous extinction. So let me briefly go to finite extinction time. So the picture you should have in mind, you also saw this. Yeah. You have around here, yeah, shrinking to a point in finite time. Yeah. Einstein metric, you see, it's positive Einstein constant. Yeah. That picture is true for any such Einstein. Finite time. Yeah. Shrinks. Now, we know the curvature goes up. Yeah. So the left side goes to infinity. Well, the 1 over b is bounded because the capital T is bounded, yeah? So the scalar curvature must lower. Yeah? So we may assume, well, go a little bit with the flow, and scalar curvature is +1, yeah? It's a constant function. So it's no yeah? Corollary. 1, suppose scalar curvature 0, +1. Yeah? Then I have another estimate, which I draw in a second, yeah. Then for all t and delta n t, delta n strictly between 0 and 1, we have norm t minus t, 1 over 8. And as above, here and here, these constants, yeah, they're not important what they are, but they only depend on the dimension. Yeah. Okay, so what does that mean? Well, you have your time 0, you have your time capital T, and then there's a uniform threshold, yeah. Delta n is between 0 and 1, yeah. So there's a gap. Yeah. That in this gap, you know, how does the curvature blow up? Yeah? So this is between, say, 1 over 8 and 1. Yeah? Of course, you know that goes to 0, clearly, yeah? When t approximates capital T. Well, therefore, you know how this develops. It's 1 over capital T. Precise description of how this term goes to infinity. Yeah? So why is that nice? Yeah? Well, it's nice because, well, what you want to understand is, in general Ricci flow, yeah, you have a Ricci flow solution, you go along, and what you hope is, well, you see always the same picture, yeah? Yeah? The same geometry appears over time, yeah? Comes, maybe it comes later again, yeah? Of course, you see there's going to be some rescaling, yeah? Up to rescaling. Same geometry comes, yeah? Of course, well, you better be sure that the picture is going to be nice, because otherwise it's called a nightmare. Yeah, so that is what you hope. Well, to understand this, what you do, well, you take a sequence of times, ti, yeah, go to the finite extinction time t, you start at this time, yeah. Well, of course, here you see the curvature is still very big, yeah. So you're not going to see anything unless you rescale. Well, what's the right factor to rescale? Well, you see it. Yeah? It is 1 over t minus ti. Yeah? That's the right factor. Yeah? Then you can hope to get in the limit something which is not flat. Yeah? It's just the right scale. Now, when you do this, it's almost all good. However, if there's only a t, there's not going to be a solution to Ricci flow. Yeah? So you must stretch in time as well. Yeah? So this is the object you want to understand, yeah? This is you, assume. Good. Now, what you consider now is your manifold. Yeah? This is a sequence of Ricci flows. Yeah? Start here. And then you hope for subconversions, yeah, I goes to infinity to a limit Ricci flow. Yeah? And you hope that this limit Ricci flow is nice. Yeah? That's a nice picture which will come over and over again. Yeah? And in this case, it's actually true. Yeah? So this homogeneous, non-flat, shrinking solid. So this is, I mean, there are of course several deep theorems, yeah. The first deep theorem is of course Perlman's non-collapsing theorem, yeah. If you zoom in here, you make sure that at time 0 for the matrix GIs, yeah, the curvature is uniformly bounded. Well, that's good in order to have the chance to get the limit, yeah. There was no chance to get the limit. Curvature blew up, yeah. However, what might happen is that the injectivity radius goes to 0, yeah. Yeah. Then there's no way to get the limit. Perlman proof does not happen. You have to get a limit. And based on that, and our neighbor later showed, well, if you have this type 1 behavior, yeah, then actually you get a limit soliton, yeah. And Anders Müller topic showed that the limit soliton is non-flat, yeah. So that these theorems, of course, are true without any symmetry assumptions, I should say, yeah. Just apply it. Yeah? I don't have to tell you what that is actually, because there is a work by Peterson, July, 2009. So if you take the thing here, yeah, this means of course the manifold can change, yeah, the limit. These guys could all be compact, that could be non-compact, yeah. And infinity, G infinity of 1, so it takes some time, yeah. This is very easy, yeah. This is EK cross Rn minus K G flat. Yeah, it's a product metric, one factor flat Rn. Yeah. Finite quotient, don't forget about the finite quotient, yeah. And this is homogeneous Einstein metric. It's positive Einstein. Yeah. So it's very easy. So this is the picture you see for a homogeneous Ricci flow, yeah, it's finite extinction time. Yeah. What you see is you run it and you see in compact homogeneous Einstein space along any subsequence, yeah, and possibly a flat factor. Yeah. That's considered to be nice. Of course, that's a self-similar solution. Yeah? If you take the guy, apply the Ricci flow, well, what happens? The first factor shrinks to a point in finite time, the second factor doesn't do anything. Okay.
So the universal cover is self-similar. I mean, down in the quotient, it might not be.
So this one is, yes, you take a finite quotient, yeah? That one is a finite quotient of that. Yeah? So it, as it stands, it is okay. Now, just very briefly, now in principle the story would be done, yeah? But when do we have finite extinction time for homogeneous spaces, yeah? Now, if Mn is compact, not a torus, yeah, then actually for all initial metrics, yeah? Yeah. Take any initial metric on a compact homogeneous space, which is not the torus, it's gonna make it to positive scalar curvature. Yeah? This is not completely trivial. Yeah? The picture is, this is the space of all metrics. This is the space positive scalar curvature matrix, yeah, plus, yeah, and you start anywhere, yeah, you make it, yeah, and then whatever. Yeah. Now, if Mn is non-compact, say, simply connected, but not Rn. Yeah? Then the picture is, well, you have a nice area where the scalar curvature is positive. Yeah? If the scalar curvature is positive, you can easily see you have finite extinction time. Yeah? However, just to show you how positive homogeneous Ricci flow is, on the result by Ramiro, yeah, much more general, on M8 is SH3R, yeah, there exists an initial metric G0 where the Ricci tensor G0 is negative. Yeah? You can have this. Yeah? Ricci tensor is negative, still the Ricci flow will move it into positive scalar curvature. Yeah? So the homogeneous Ricci flow on this space is so good, yeah, that even a metric with negative Ricci curvature after some time has to become positive scalar curvature. Good. When did we start actually?
940.
9:40. Okay, then I have time for two questions, because afterwards I go to the immortal case. I mean, well, there's of course the question hidden. I'm gonna come later to. Yeah. Other more obvious questions are, as we learned, I guess, in Toby's talk. Yeah. What about uniqueness? Yeah. There's this limit soliton. Is it maybe unique? Yeah. Of course, that's the best scenario. Yeah? You run a Ricci flow, and then you see always the same picture. Yeah? There's not the thing with the subsequence, yeah, and picking a subsequence and so on. It's really stabilizes. Yeah? We only know that if there's no flat factor. Yeah? If the limit is compact, then that's true. Yeah? It's a unique limit. Yeah? And the reason also kind of, Toby said it already, it's in this case very, very easy. The volume normalized Ricci flow, yeah, on a compact homogeneous space is a gradient flow of an analytic function. Yeah? And therefore you have a Liouville inequality, yeah, and that gives you, if the omega limit set of such a flow is non-empty, it's unique. Yeah? It consists of a unique point. Yeah? That's very nice thing. In general, we don't know, of course, it's kind of expected. Yeah? Another thing, of course, which is maybe more interesting, well, the limit compact factor should, of course, somehow be related to the homogeneous space you started with. Yeah? I mean, they cannot be completely independent. Yeah? And kind of what you hope is, I mean, it's a vibration, so to speak. Yeah? You see the space, the compact factor inside, yeah? The homogeneous space. So there's a kind of a sub-manifold, yeah? EK, yeah, and transversal, you have a flat factor. So these are two open questions. Good, so far, that's finite extinction time, yeah, and now I want to move on to, yeah, flows which live forever, yeah. Remember, of course, all that, yeah, would not have been possible without Hermann's non-collapsing theory. Right? No way. Yeah. First of all, and secondly, also the shrinking solitons, which are actually gradient, that's for the experts, yeah. Do we have any chance to see those? Yeah. Okay. Now, what about, it's called the immortal case, yeah? What's an example? Well, I don't give you the non-compact space because that's, you don't see it really, but I give you a compact motion, yeah? You start, so metric of constant curvature -1, and you ask what does the Ricci flow do? Well, if you look at the equation, it's very easy, yeah? Stretches the thing. Yeah? Lives forever, makes the thing larger and larger. Yeah? It's just a rescaling. Yeah? And of course, what you can do as well, you can cross it with S1. Yeah? But the factor of the S1, I don't change. Yeah? Well, of course, the product structure is preserved, here it gets large, yeah, but the flat factor stays constant. Yeah? So look at this. We're going to need this in a second. Yeah? So that's, if you go to the universal cover, of course, then, but then you don't see the curvature. Now, well, it's easy to see, since the flow lives forever, cannot enter positive scalar curvature. So if it would make it to positive scalar curvature, it would blow up in finite time. So you know the scalar curvature is less or equal than 0. And even better, if the scalar curvature would be 0 at some point, can it make it positive? You see the illusion equation, then it must be Ricci flat plus homogeneous, and then thanks to Dimitri Alexeyevsky, yeah, it's going to be flat. Yeah? So, well, flat Ricci flows are not that interesting. We understand that, so we can assume the scalar curvature is negative for all t. In particular, of course, we can rescale at the beginning so that the scalar curvature is -1. And from the 0 in A, get another corollary. Suppose scalar curvature 0 -1, then times t en for all t. Yeah? So now you have this growth rate, yeah, which is to be expected, yeah, so that says that t, of course, gets very large, yeah, so that means this gets very small, as in the example, yeah, it's like 1 over t, but precisely at this rate, yeah, it's called a type 3. Good. So, and then, of course, you do the same thing as here, yeah, it's the very same thing, yeah. You have the capital time t, which is now, of course, plus infinity, yeah. Okay, make it finite, yeah? You take your points ti converging to capital T, yeah? And then you rescale again at the level of the curvature. So that means in this case, you take 1 over ti g of ti times. Yeah? It's the same thing, so to speak, yeah? Go further out, yeah? And then you have to rescale to see something. Yeah? If you don't rescale, you don't see anything, yeah? It's flat. Okay. And then, of course, the hope is again, well, you're going to see something. And you do. That's the second theorem I'll talk about. This is called Miro. Yeah, same situation as here. You have the sequences, yeah. And they're gonna subconverge. I mean, I didn't tell you here, of course, what did I mean. Should be more precise here. It was, of course, in pointed Gromov topology, yeah. It was very vague. Geometries, yeah, converge. I want to make it formally, yeah. There are different morphisms involved, of course. You have to fix a point, a base point, which is arbitrary because the space is homogeneous, yeah? Now, this subconverges, I'm going to tell you in a second where. Again, to a limit homogeneous Ricci solution, which this time is homogeneous, expanding. Or, just to warn you, or flat, yeah? I mean, let's say flat would be included, but just to make it clear, in this case you can't have flat limits, yeah? There is no way out, yeah? So that 0 you cannot improve, yeah? You maybe have wondered, there was a 1 over 8 there, yeah? There's a 0, can you do better? You can't. Yeah? Okay, now let me explain where is the subconversion, because this example clearly shows you if you rescale at the level of curvature, what's going to happen? Well, these guys got large, yeah? The curvature went to 0. If you rescale it, well, they stay constant, yeah? They don't move at all. However, the poor is 1, well, gets smaller and smaller and collapses, yeah? So there is no non-collapsing theorem, yeah? For immortal solutions of Ricci. It just can't collapse. So therefore, you can never get pointed Gromov without any assumption, yeah? And there are no assumptions whatsoever. So this is what John Locke calls, in the sense of Riemannian groupoids. John Locke. Yeah, since I'm here in Florence, yeah, I will explain what that means in this very special case, because it's not the fancy thing for homogeneous spaces, yeah. And yeah, there's a good reason for explaining it. So suppose these matrices GI, T, yeah, have small injectivity radius. Yeah? These are our enemies. Yeah? So there's a very small S1. Small closed channels. Yeah? And by the rescaling, well, of course we may assume that at the level of curvature, sectional curvature is bounded, yeah? Say by 1. 1. Less or equal than 1, yeah? Bounded curvature, but small integral. You don't get a limit. However, you pick your favorite point, pi, then of course you have the exponential map on pi, and you know, because the sectional curvature is bounded, well, if you start at pi, there are no conjugate points before distance pi. Yeah? So, comparisons. So that means you lift the same, yeah, to the tangent place, let me call it G hat 1. Well, these are metrics on the ball of distance pi in the tangent space at this point, which are, of course, locally homogeneous. Yeah? You pull back a homogeneous thing to something which is not complete. This is not complete, yeah? But, of course, between any 2 points, yeah, you're going to find a symmetry in the neighborhood which maps the one neighborhood to the other. Yeah? Well, this convergence means then only that on this fixed ball, yeah, you're going to converge to a limit. Yeah? On the same ball. Yeah? In C infinity. Yeah? No differential whatsoever. Yeah? And this guy, I should say, is complete. Yeah? Yeah? This means that you show that this space, this limit soliton, can extend it to a globally homogeneous space. It's part of a globally. This is not true, I should warn you, for any homogeneous space. Yeah? If you take S3 cross S3, if you take your favorite torus S1 in the maximal torus S1 cross S1, but which irrational slope. Yeah? It's not compact. It's not compact. You get a locally homogeneous space, yeah, which you cannot extend it. Yeah? There are even, I guess, by work of Wolfgang and Mackenzie, there are even Einstein metrics, yeah, on these guys, yeah. But they don't fit in a complete space, yeah. It's only a local thing, yeah. But these limit guys you can extend. Okay. So, of course, you might say, well, so this collapsing thing is, of course, not so nice, yeah. Can we get rid of it?
So why is the word groupoid in there?
Sorry?
Why is the word groupoid in there?
John? Well, I guess if you do it at many points, yeah, of course, in the general case, yeah, you do the same thing at any point. And of course, but you have these models, yeah, then 2 different points, but of course you have to say how you identify it, yeah. Clearly, if you take a neighboring point, you have the same picture, but in the picture you get, then you have to say how this is identified.
So the relevant groupoid would be the possible transition functions between these, which they don't form a group because
But morally, it's you do this at any point and then you identify. Okay. So what are examples? Yeah. So that's the first corollary. Where do we have such a solution? First of all, yeah, I didn't tell you. Where are the model solutions? And then maybe even better, well, can we improve this, well, kind of bad thing, yeah, to point the cheater problem so that we do not have collapse. And actually we can, if Mn is diffeomorphic to Rn, then for all initial metrics, yeah? I mean, I don't give you the algebraic structure. I don't only give you the topology, yeah? You're going to see in a second there are plenty, it's a huge number of different algebraic structures, yeah, on this space Rn, yeah? Doesn't matter which one, yeah? First of all, the solution is immortal. Is immortal for all. Second, it's non-collapsed. So we can get bounds, we can prove this cannot happen. So you get their convergence in pointed Giga Bohm of the point. Yeah? This is really, you see the limit as you expect, as you hope. Now it's even better at this point. These are the only known immortal homogeneous solutions. There are no other solutions known on simply connected. Yeah, you can of course take quotients. Yeah. As here, of course you can go from R to S1. Yeah, but simply connected, there are no further examples. Good. Yeah, maybe here I should, of course, mention previous work of John Lott, I guess in 2007. He worked on the 3-dimensional case, then partially on 4-dimensional case. Then Jorge Lauret, 13, he did the nilpotent case, and Romina Royo did a very special solvable case, yeah, where the nil radical is a B, yeah, and then that's also a very special case, yeah. Maybe I forgot something, but so there was previous work, but of course not without any assumption. Now, okay, let me say I didn't tell you what these guys are. Yeah. What is this? Yeah. Let me know what's known. All known homogeneous expanding Ricci solitons are either solved solitons, I'm going to explain the term in a second, or, I mean, just like do the solve Einstein solve manifold. Yeah. So that means the manifold Mn, if you assume it's simply connected, is of course Rn, and is a solvable Lie group, yeah, which is acting simply transitively. Yeah. These are all known examples of homogeneous Einstein matrix with negative Einstein constant. And the same is true for these solitons. Yeah. That's a famous Alexevsky conjecture saying that's it. Yeah. There's nothing more. Yeah. Maybe this is in a strong version. Yeah. Maybe it was formulated a little bit weaker. Yeah. They must live on Rn. Yeah. But there's a conjecture saying, well, yeah, these are left invariant matrix on a solvable Lie group. Yeah. These are the only homogeneous Einstein matrix and the only homogeneous expanding solitons. Yeah. So suppose you are on such a Lie group which admits an Einstein matrix. Yeah. Does the Ricci flow find the Einstein matrix? Yeah. So the picture is fine. And here, very sorry. I apologize for not quoting many work on this deep subject. It would be just way too long. So I should mention work by Jens Heber. I guess it was maybe 1998. Long Inventiones paper. Yeah, we developed a deep structure theory, and then maybe Jorge Lauret 2010, yeah, analyst paper, yeah, where he kind of classified and showed that all these guys are standard. So I mean, the deep results, yeah, on the structure of these Einstein metric plus negative Einstein cost on top of it, yeah, very nice deep results. Much more has been done, yeah. Apologize for not being able to say more. Yeah, so on such a guy, what does the homogeneous Ricci flow do? So that S, G, B, here, Einstein, solve manifold with at the point you still need, I mean, it's not flat. And then I give you a picture. Then 1 over T. Then for all initial metrics, converges to phi star. Of course, maybe multiplied by a constant. Yeah? So there's a normalization involved. I'm not going to tell you. So there's your Einstein metric G. Yeah. Jens Heber proved it's unique. Yeah. Somehow. Well, there's an orbit, yeah, of isometric ones, yeah, they are different as metrics, but isometric as Riemannian structures, yeah. And what this says is, wherever you start, yeah, you're gonna find that orbit. Yeah. So it is clearly, that means that this is the best metric, yeah, on that homogeneous space. In particular, of course, that applies because the convergence is really in C infinity here. It's on this finite dimensional space of metrics. That the isometry group of G naught, which I told you does not change over time, must be contained in the isometry group of that limit. That result was proved previously by Jablonski, Mike Jablonski, Carolyn Gordon. 15, yeah, saying that isometry G naught is contained. Yeah, so P star. Yeah. They use completely different methods. Yeah. They prove this as right. Yeah. But from the flow method also. There's a similar result for the soliton case, for the true soliton case. Yeah. There, it's not true that you get C infinity conversions, but the Ricci flow also finds it there. You get point to Ricci conversion. But that's, of course, kind of the best you can really go for. Converges in this finite dimensions. Good. So, I mean, in short, I'd say, summarize this and then kind of, you want to also forget it. It's as good as it gets, yeah? You take a homogeneous Ricci flow, you go to the extinction time, you rescale on the curvature level, and you see, if you go to a subsequence, you see a soliton, yeah? In the finite extinction time, you see a shrinking soliton. In the immortal case, you see an expanding soliton. Maybe there's a price to pay. Yeah? You have this collapse in there. We cannot exclude because we do not know, for instance, sorry, I'm here to say this, we do not know whether SL2R cross SL2R admits an Einstein metric of negative scalar touch. Yeah? That is not known. Yeah? And, well, there could be type 3 solutions on SL2R cross SL2R, which are immortal, could be, yeah, but collapsing. Yeah? We don't know that either. Yeah? So, that's as it stands, yeah? Good, so let me explain where, how could you possibly see these expanding solitons, yeah? What does go in, yeah? And there's a geometric part, I mean, at least for me, yeah? Which, for the, well, I guess for Jorge and Ramiro, it's not geometric, it's also algebraic, but for me it's geometric, and then there's of course a deep algebraic part. Yeah. So let me say something on proof. Yeah. So I didn't tell you, but of course, for a homogeneous space, the space of matrix is a finite dimensional space. Yeah? And that we do this only, say, for Mn is a Lie group. Yeah? No isotope. Yeah? Then you know that the space of homogeneous matrix, well, what is that? It's a space of positive definite scalar products. Let me call it Pn. Or Dn. So this lives in the symmetric. I think about matrices. Yeah, this lives in the A transpose is A. Yeah? Symmetric anamorphisms or symmetric matrices, of course. Yeah, and as a homogeneous space itself. Yeah. Take out the determinant. It's a symmetric space of non-compact type. Yeah, SLN over SON. Yeah. And the Ricci flow, of course, G naught, yeah, GT. Well, it's just, I mean, the Ricci flow is not a PDE, yeah? It's an ODE, and it gives you a solution on this space. Yeah? This is what it is. Yeah. Now, yeah, let me write this: d over dt, GT minus 2 Ricci flow. That's an ODE, yeah, if you want. And you want to understand the long time behavior of that ODE. Now, part 1 here is what I call the Uhlenbeck trick. Right? So, of course, I mean, I used to think about this, yeah, as a homogeneous Ricci flow. And well, what's the geometric data? Well, the geometric data is you have a Lie bracket on the Lie algebra, yeah, giving by left invariant vector fields, yeah, on the group G, yeah, and let's call this new stuff, yeah. These are the data, yeah. Geometries are changing, but the algebraic data is fixed. Yeah? Now, what does the Uhlenbeck trick? So the Uhlenbeck trick is, well, what you want to do is, if you consider Ricci flow on channel, yeah, you notice that if you fix a coordinate frame, yeah, at time 0, which is say orthonormal at the point P, well, it may not be orthonormal, of course, if the metric evolves. Yeah? Clearly, that's bad. Yeah? You want to take frames which stay orthonormal, because then the evolution equation is simpler. That's called the Uhlenbeck trick. Yeah? So, kind of, you want to fix the geometry, yeah? The initial geometry. Yeah? So, that amounts to say that the GT, yeah? Well, you want to write it with respect to G0 in an anamorphism HT. Yeah? HT, so to speak, is square root of G. Yeah? You write this as this, yeah? And then you ask, well, what do I have to do, yeah, so that this solves Ricci flow, and you find H prime of T minus H of T. Capital Ricci of T, yeah? That's the Ricci endomorphism, yeah? Only for specialists. It's a linear ODE, yeah? It works in complete generality, yeah, without any symmetry assumptions. So what you do with it is, well, you solve the Ricci flow, you get a one-parameter family of matrices. Therefore, you get a one-parameter family of Levi-Civita connections. Yeah? You take, by this trick, you pull the Levi-Civita connections back, you get a one-parameter family of metric connections, not necessarily torsion-free. Well, you take torsion, you anti-symmetrize in the first two arguments. Well, what do you get at one point? At one point, you get an element which is anti-symmetric in the first two elements. It gives you a vector. Yeah? You get an element in Vn, lambda 2, r and star, tensor R. Notice the bracket is just the very same thing. Yeah? You plug in two vectors, it's symmetric, you get a vector. Now, when you do this, yeah, you can move the Ricci flow from this side to the other. That means maybe now another sloppy, yeah. So of course there's a mu star, yeah. And yeah, now I'm skipping a little some details, yeah. What you can do actually, you can take the entire orbit and embed it. Yeah? So the space of all metrics, in this baby case, yeah, you can embed it as an orbit, GLN, mu star, say O star. Yeah? In this space, yeah. So rather working with metrics, you're working with connections. Yeah? Of course, it's kind of clear this is one-to-one. Yeah? You know the connection, you get the metric and vice versa. So, yeah, there should be two-dimensional. Yeah? Now, if you translate this equation, of course, you get the equation for connections. What is it? d over dt mu t is minus pi brick mu t times t. That's called the bracket flow, yeah, introduced by Jorge Lauet. Yeah, this is one-to-one, and I'm going to tell you in a second what that is, yeah. So you can translate it. So kind of now the brackets change, and then there's another trick. Yeah, you fix a background metric here, and you break symmetry. Yeah, you break symmetry. This gives you a scalar product, and this scalar product gives you now a fixed scalar product on the space. Yeah. Fix the scalar product, change the brackets. Bracket fixed, scalar products change. Yeah. Go from one to the other. What is that? Pi s mu is actually a linearization of the action, of the natural action. Yeah? Didn't tell you what that is. What is that? It's just s mu minus mu. Yeah. S symmetric. Yeah, that's the linearization of the natural action GLN on the cell. Okay, so this is undecked, this is in principle geometric, yeah? Geometers know this quite well, so you don't get any detail here. This is not a deep thing, yeah? Now, why should that be an advantage, yeah? Yeah, you work with the space of metrics, now you embed it in this higher dimensional space, it's an orbit, yeah? Why? What do you get from this, yeah? So now here is where geometric invariance theory comes in, yeah? Let me briefly something about that. GIT, geometric invariant theory. For the GLN action on the X. Yeah, to give you an example of such an action, consider the following action on R2, yeah, by R. Yeah, so that's a famous picture. There's three types of orbits. Yeah, versus 0. So linear action, yeah. Then you have these hyperbolas, yeah. And then there are four special ones. Yeah. See if one of the guys is 0, yeah. It's just scaling, yeah. So that's the orbit space. Voila. So these orbits are closed. Yeah, these are closed. The red ones are open. So there are closed orbits and open orbits. Even worse, if you take the two red ones here and go to the orbit space, you cannot separate them. Meaning the orbit space is not Hausdorff. It's the way it is. You think, well, that's really bad news, for a geometer, assuming about isometric action. But this is what it is. So this is bad news, if you want. The good news is, I'm very short here. So the non-compactness of GLN is a billion. So what do I mean by that? You have, of course, GLN, and then you have a polar decomposition. You can write any invertible matrix as something orthogonal plus something positive definite. This is a diffeomorphism. Now, something which is symmetrically positive definite, of course, you can diagonalize. So you keep going, you write this as ON times, Tn. It's not a compact torus, times ON twiddle, and this is now, of course, it's a non-compact torus, It's diffeomorphic to Rn, So you see, compact, non-compactness is abelian, This makes the thing running, Of course, any geometer, abelian group, linear representation, you can diagonalize simultaneously, and then, of course, you can say something, And you do it for the tori, and then you, it's very clever, But this makes the thing run, So just to give you a taste, what can be done? So the space En, now this is true complete generality, we only need it for this representation space. You take out the 0, can be written as a disjoint union, finite, as betas, where these guys are GLN invariant submanifolds, possibly of different dimension, with remarkable properties. I'm not going to give you the remarkable properties, it's highly remarkable, What I want to tell you is what is the set B? Where does the finite set come from? Which gives you these strata. Well, in this thing is a moment map. And so to the symmetric n by n matrices implicitly given by m mu s. There's a natural scalar product. Of course, this scalar product induces scalar products of all sorts of tensor functions. So implicitly given by, well, you consider the action, the action field, pi mu, pi s mu, So as a geometer, I would like to think about this as a killing field. You have a one parameter group acting on the space. Gives you a killing field. Is of course not a killing field. But then you measure. How does the distance function change? Under this action. So there's this moment map, and from the moment map you get the energy. The energy F, Vm 0 R, well, mu take m squared. That's the energy. And now the highly remarkable thing is, this thing has only finitely many critical, not points, but values. Let me say this, the values, they come not isolated, they come as orbits. On, beta 1, on, beta 4. Okay, whatever. So these finitely many guys give you that. That gives you decomposition, And now let me, in the remaining 10 minutes. Let me just give you a little taste, yeah, how you can use the Ullbeck trick, yeah, which shifted the thing from matrix to connections, and now the GIT on the space of connections. How could you use that to detect an expanding Ricci soliton, yeah, for homogeneous Ricci? Okay, so of course we have this orbit. Yeah. These guys are Chilet invariant, so the orbit lies in one structure. Yeah. This orbit lies S beta. I could call it S beta star. Yeah? Let me remove the star here. Not whatever. Yeah. So this is kind of the and now. Okay. This beta. Yeah. How can you use it? Yeah. Good. So there are now several steps. Step 1. Step 1 is, of course, you need to compute the Ricci tensor with help of the metric G, yeah, and the left invariant vector fields. Yeah. Here, of course, you also can compute the Ricci tensor. Yeah. You have this fixed scalar product and the bracket, so there's a Ricci tensor. Yeah. So the Ric mu is the moment map. Not quite, but almost. Non mu squared plus something which is quadratic in mu. Yeah? And of course, you could say this is nuts, yeah, because well, you can always add it and subtract it. Yeah? However, let me tell you, this is natural. Yeah? It comes naturally this way. Yeah? We're going to need this in a second. Yeah? Yeah. This is quadratic, of course. This is scale invariant. Yeah, that's quadratic in mu. And the Ricci tensor is quadratic in the connection. Yeah, nabla nabla. Yeah. Okay. Now step 2 is well, this GIT. This is so powerful that you don't only get these as betas. Yeah, and which are GLN, you get estimates. Yeah. Give you estimates which involve the moment map. Yeah? You know that M mu, and now the beta comes into play. Yeah? Beta plus norm beta squared identity is bigger or equal to 0. This is GI. Yeah? It gives you an estimate. Now, because I told you this is natural, yeah, this is only to give you a taste, yeah. The truth is like, yeah. This is far more complicated. But just to get where does it come from. Now, because this is natural, yeah, this inequality, you can shift the full Ricci tensor, not quite. Big star. Yeah. Specialists know what the star means, yeah? You just forget about the star. Yeah? This is the Ricci. You get an estimate for the Ricci. Yeah? Yeah. Which is perfect, yeah? You could not see this on the space of metrics. Yeah? Now the step 4. Now you need the scalar curvature. Scalar curvature, forget about the star, sorry. Yeah? Non-positive. Then you get a very nice estimate. The following form. Yeah. Let me stress this. Yeah. Oh, that should be a minus. Yeah. So what does it say? Well, it says on this orbit, so to speak, if you take the norm, the best Ricci curvature in upper is the beta. That's the optimum. Enormous. And equality, that's, once I have this, now let's do the next step. That's even more remarkable. Step 5. Equality, if and only if mu is a solid. So this again uses, of course, the sides of Re and Lafuente and Mike Jablonski. But just let me give you a little taste in this case. Well, if this sharpness here, yeah, sharpness means, of course, that we had sharpness here. Yeah? This was 0. Now let's go to the definition of the moment map. Yeah? So this is 0. Yeah? So this is the S over there. Yeah? So we plug in the S. So this is 0. Pi of this guy is 0. Well, if this is 0, this means there's a derivation. Yeah? You see a derivation. Well, once you see a derivation, yeah, you see maybe a one-parameter family of automorphisms, and you see a one-parameter family of diffeomorphisms, yeah, and there's a solid. I'm sorry. but I mean, yeah, you can see how strong this is. Okay. In the last 2 minutes, yeah, let me move on. Now, of course, well, Tim, you're extremely happy. Yeah? You have estimates which are sharp on solitons. Yeah? That's fantastic. And then, well, of course, you hope. Step 6. Fine. Scale invariant. Lyapunov function. Yeah? Which goes down strictly unless we are on a solid. Now when you think you're done, well, you're not. That was known for many times. The problem is your T may blow up. Yeah? There's nothing you can do about it. It may blow up. Yeah? So you don't get you cannot, because of the scaling invariance, it may head off to infinity. In that case, you cannot handle it. And it just happens. Yeah? There's nothing you can do. So the trick around is, now we come back to geometry. Pick a sequence Ti going to infinity, such that, of course, the MMGIT, they subconverge to our limit, plus, we take a limit which has highest isometry group possible. In isometry group T infinity 1 maximum. Of course, the isometry group, the dimension of the isometry group is bounded. Take a sequence where this is maximum. So that is the way restart Ricci. With that guy. And now I just say this, restart it. And then, of course, if you go to the limit, you know, in the limit, the isometry group cannot go up. If it would go up, then you need, you have the principle in ODEs, what the limit of a limit is a limit. Then you would have constructed, of course, a limit which has higher isometry. So this cannot happen. This cannot happen. We call this algebraic collapsing. I'm running out of time, so I cannot go into it. It's quite interesting phenomenon. Everything is fine, geometry is fine, everything, but the algebraic data collapse. You start it again, and for this flow, you prove the theorem. In the limit, there is a solid. Now, remember, there could have been collapsing, yeah? So you get it only locally. At the end of the day, you must prove that this local soliton can be extended to a global soliton. This is similar to the work of Spiro, which proved that also a locally homogeneous Ricci flat metric is flat. Yeah? There's a beautiful proof by Ernst Heinze, yeah? Using the splitting theorem, yeah? I guess wrote that, yeah? That the Ricci flat homogeneous space is flat, yeah? It's very easy to see using the splitting theorem, but of course for locally homogeneous, you can't do this, yeah? So there's an extra argument, yeah? And a similar argument works here, and you get that these guys in the limit are globally homogeneous. Yeah, maybe that's a good point to stop. Thanks.
Questions?
So for convergence in the immortal case, you had to sort of resort to this language of groupoids and so forth. Is there any reason to believe that when you pass the universal cover, you won't be able to prove eventually that you get Cheever-Gromov? Cheever-Gromov?
I mean, yeah, if the Alexeyevsky projection turns out true and even more, then we would be able, we would know type 3 solutions only exist if the universal cover is Rn, and therefore it would be non-collapsing, yeah. But also, even if you would not know this, it still might be true. I agree, yeah. Yeah, is there collapsing or not? We don't have an example where, of course not, yeah. The only known examples are on Rn, yeah. And that's maybe a good point. Let me mention this because this is a nice problem. So apparently it doesn't seem to be known whether on a solvability or on a homogeneous space, diffeomorphic to Rn, can it have closed geodesics, yeah? This does seem to be an open question, at least I don't know. So if you could exclude that, yeah, at least for this, we know they cannot be short, curvature is 1, they cannot be very short closed geodesics. That we can, but maybe they are large closed geodesics.
Questions?
Is the criterion with maximal interval is already t equal infinity or t is finite?
Is there?
This t, you consider the maximal interval,
yes.
0 to t, and where t is infinity or not? Is there some condition?
Well, if the manifold is compact and not a torus, the t is finite.
Yeah, but for non-compact.
For non-compact, yeah. Well, I mean, you may speculate, of course, actually, that the homogeneous space tells you for all initial metrics. Yeah? For the Rn, if the space is Rn, then it's always infinite. Yeah? Because the scalar curvature for any metric, as you know, is non-positive. Therefore, the solution must, the scalar curvature is negative for all times, and therefore it's immortal. Yeah? Of course, on the other spaces, as the picture indicated, we don't know. Yeah? We do not know whether on SS3R there's an initial metric, yeah? Another initial metric, which is immortal. Yeah? Of course, Einstein metric on SS3R would be a counterexample, clearly. Yeah? But also, if there's no Einstein metrics, yeah, we don't know. Yeah? So it would be nice, of course, if the Ricci flow kind of always makes the positive scalar curvature. Yeah? If there is positive scalar curvature, that would be a very nice result.
More questions? So what about the one?
The wine.
The wine. Thank you.